Let's move on towards our next theorem from matrices unit of mathematics. So all the positive odd integral power of a skew-symmetric matrix is skew-symmetric, whereas all positive even integral power is symmetric matrix. What does it mean? Suppose we have a matrix A which is skew-symmetric. Suppose we have a matrix A which is skew-symmetric. Now, if this matrix A is skew-symmetric, if we raise the power on this matrix, if we raise the power, suppose we raise the power n, we raise the power n. So what it is saying is that if n is odd and A is skew-symmetric, then A to the power n will be skew-symmetric, okay. And if n is even, then A to the power n will be symmetric. If n is even, then A to the power n will be symmetric instead of skew-symmetric. It will be symmetric. So that is what is the theorem saying. Now let us try to prove this particular theorem. Let A be a skew-symmetric matrix. Let A be a skew-symmetric matrix. There is one mistake over here. This is not the correct thing. Just remove this while making the notes. Of order n. This is incorrect. Okay. Just remove this while making the notes. Okay. Now you can have a look. Now it is correct. Let capital A be a skew-symmetric matrix. Capital A is a skew-symmetric matrix. And a small n is odd positive integer. Small n is odd positive integer. And whenever an integer is odd, we can write it to be 2k plus 1. We can write it to be equal to 2k plus 1, where k is any natural number. Okay. So if you take k equal to 0, n will be equal to 1. If you take k equal to 1, n will be equal to 3. If you take k equal to 2, n will be equal to 5, and so on and so forth. Okay, so in order to represent odd number, we can use the notation 2k plus 1. And it is also given to us that capital A is skew-symmetric. So as it is skew-symmetric, so A transpose will be equal to minus A. As it is skew-symmetric, so A transpose will be equal to minus A by definition of skew-symmetric matrices. Okay. Now what does it mean by A to the power n? What does it mean by A to the power n? So you can have a look. A is skew-symmetric, so A to the power A transpose is equal to minus A. Now if we take A to the power small n, where n is odd, over here n is 2k plus 1, n is equal to 2k plus 1, where k is any whole number. K is what? K is whole number. Okay, k is whole number. That is whole number means 0, 1, 2, 3, 4, 5, like that. Okay, starting from 0 full figures. Okay, so that is the meaning of whole numbers. So k is a whole number and small n is an odd number. So odd number can be represented like this. Now this small n has been written, its transpose is being taken. Now when we take its transpose, let's not forget the definition of power. What does it mean by power? Whenever we raise the power on something, it means that particular entity multiplied that many number of times. Okay, so capital A to the power small n, capital A to the power small n will be capital A multiplied by capital A multiplied by capital A multiplied by capital A. How many times? N times. It will be n times, right? So A into A into A into A into A n times, and the transpose of that particular entity. Now we already know that what do we know? We already know that AB transpose is equal to what? AB transpose is equal to B transpose A transpose. This property we already know. So by using this particular property, what can we get? So applying this property on this particular thing, this A will become A transpose and come in the front. The second last A will become A transpose and will come here. The third last A will come over here and become A transpose. The first A will go in the last. The very first A will go in the last and become A transpose. The second A will go in the second last and will become A transpose. The third A will be going the third last and will become A transpose. Okay. So it is equivalent to A transpose multiplied by A transpose multiplied by A transpose and so on and so forth up to n times. It will be n times. So A transpose into A transpose into A transpose. How many times? N times. Now from the definition of skew-symmetric matrices, what do we have? From the definition of skew-symmetric matrices, A transpose is equal to minus A by definition of skew-symmetric matrix. It is given that A is skew-symmetric, so A transpose will be equal to minus A. So replacing this A transpose with minus A, replacing this A transpose with minus A, replacing this A transpose with minus A, and so on and so forth up to the last element. So n times. Okay. Now you can take out the minus sign common from all these things. The minus sign from here, 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 here. So minus 1 to the power n will come. Okay. So it will be, if you take out the minus sign common, it will be minus 1 to the power n. And n is equal to 2k plus 1. N is equal to 2k plus 1. So minus 1 to the power n will become minus 1 to the power 2k plus 1. So minus 1 to the power 2k plus 1. And if you remove the minus sign, then a will remain. So a into a into a into a into a, how many times? N times. A into a into a into a, how many times? N times. So n times. And minus 1 to the power 2k plus 1, it will become minus 1. Because we already know this particular fact. We already know this particular fact that minus 1 to the power odd number. Minus 1 to the power odd number is minus 1. And minus 1 to the power even number. Minus 1 to the power even number is positive 1. So minus 1 to the power even, minus 1 to the power even is plus 1, minus 1 to the power odd is minus 1. So over here it is minus 1 to the power odd. So as it is minus 1 to the power odd, so it will be minus sign over here. It will be minus sign over here. And a into a into a, how many times? N times. So it will be a to the power n. Now have a look at this particular expression. A to the power n transpose is coming out to be equal to minus a to the power n. Okay, a to the power n transpose is coming out to be equal to minus a to the power n. Now let us assume that this a to the power n is equal to c. This a to the power n is equal to c. Let us suppose that a to the power n is equal to c. So minus a to the power n means minus c. Okay, so c transpose is equal to minus c. Now whenever c transpose is equal to minus c, it means that c is skew-symmetric. It means that c is skew-symmetric. Okay, so now but in the place of c, it is a to the power n. In the place of c, it is a to the power n. So a to the power n will be skew-symmetric matrix. A to the power n, therefore a to the power n will be skew-symmetric matrix. That is what we can prove from here. A to the power n is skew-symmetric. Similarly, we can show that if n is even, if this small n, if it is even, then it is a symmetric matrix. In the very similar fashion we can show this. In exactly similar fashion we can show that if n is even, then it is symmetric matrix. What will be the difference? The difference will be that instead of this particular entity, if we prove it for n is even, then instead of this entity in the circle, this entity will appear. Okay, and if minus 1 to the power even is there, it will be equal to plus 1. Okay, so this minus sign will not be there, and if that minus sign is not there, then it will be symmetric. So for n is equal to even, for small n equal to even, a will be symmetric. Okay, so similarly we can show that if n is even, then it is a symmetric matrix. That is, capital A is a symmetric matrix if n is even. In a similar fashion we can show this particular thing. So hopefully you got the thing.